On Friday, we had looked at solving or finding the inverse of a 2 by 2 matrix by, first of all, considering the fact that any matrix times its inverse will equal the identity. So we wrote this equation here using A, B, C, and D. Then we multiplied the left side together and found that if we get this matrix, then A plus 4C has to equal 1, and B plus 4D has to equal 0, and so on. We came up with this system of 4 equations with 4 unknowns. Now, the nice thing is those 4 equations weren't too hard to solve because 2 of the equations only had 2 variables and the other 2 equations had the other 2 variables. So that made it a lot easier for us. But we got our inverse as -3, -4, 1, 1. Okay. Now, I want to kind of focus in on what we have here after we multiply, because this actually is where we get our second method. Now, you wouldn't need to multiply in order to get this, but you can see why we're allowed to do what we do here in our second method using an echelon form. If you look closely here, you'll notice we have a 1A and a 4C. We have a 1B and a 4D in our first row. You notice they have the same coefficients, even though the variables are different. Okay? Down in the second row, we have a -1A and a -3C. We have a -B and a -3D. So again, we have the same coefficients with different variables. And what we're doing here is we actually took those coefficients, 1 and 4 and -1 and -3, which happen to be the original, those are the original elements of the matrix A. And we're going to put this in here with our identity matrix. And really what we're doing is creating it's called a double augmented matrix. If you remember, the augmented matrix was when we had a system and you use the constants. Here it's like we have 2 sets of constants and they happen to be the identity. Okay? So what we do is actually set up our matrix like this with the original matrix on the left-hand side, okay, and our identity matrix on the right-hand side. Okay, and then what our goal is to get to a matrix where the identity is actually on the left-hand side. Okay, so it's almost like we're using row-reduced echelon form to get the identity from the right-hand side to the left-hand side. And what ends up happening is the elements you end up with on the right-hand side will end up being your inverse. Okay? So while here you had A and your inverse, here you have your inverse, or I'm sorry, your identity and your inverse. Okay? So over there you had the matrix and the identity. Now you have the identity and your inverse once you get it over there. So let's actually get it to that point. Alright? We're going to use the same method that we did when we were solving a system using row-reduced echelon form. Okay? Except now instead of solving a system, we're using that same strategy to get an inverse matrix. Yes?
We got that from our previous problem, right? The actual...
Yes, we know what the answer is supposed to be because we just did this problem up here.
Okay. You can do it without knowing the answer.
Yeah, you'll do it without knowing the answer. Okay? Nothing that I do here is going to assume that I already know what the answer is. Alright, so we'll just use our normal strategy here. First of all, get a 1 in the top left corner, which we already have. And then when we're doing row-reduced echelon form, what's the next thing that we would do here?
Yeah, 0.
Get a 0 in the rest of the first column. So if I want to get a 0 here, Good. Row 2 plus the row 1. Okay. Row 1 is going to stay the same. But when we add row 2 and row 1, we get a 0. Negative 3 plus 4 is 1. 0 plus 1 is 1. 1 plus 0 is 1. Okay? So we got our 1 in the top left corner. Then we got our 0 in the first column. Now we need to get
0 in the second.
a 1 in the second column, which we already have. This one turned out really easy. We already have the 1 in the second column, so now we need the last 0, where this 4 is. Okay? So if I'm going to change row 1 by using row 2, how am I going to do that?
Minus 4.
Good, a minus 4, row 2. So I have 0, 1, 1, 1. And then look, 1 minus 0 is still 1. 4 minus 4 is 0. 1 minus 4 is negative 3. And 0 minus 4 is a negative 4. And you'll see we ended up where we were supposed to. Okay? But even if we didn't know that in the first place, we see right here, here's the identity matrix on the left and the inverse matrix on the right. Okay? So that tells us
So that's the second way to get the inverse.
this is the second way to get the inverse. Okay? The inverse of matrix A is negative 3, negative 4, 1, 1. Okay? And the reason why I'm showing you this is because it doesn't just work for 2 by 2 matrices. It works for 3 by 3 matrices and 4 by 4 matrices and so on. Okay? It works for any square matrix. Yes?
Which is, do you think is better, this one or the first one?
Honestly, with these two methods on a 2 by 2, it's about the same. Okay. Now, once you get to a 3 by 3, honestly, I've never used the first method to do a 3 by 3. I've always just done this method. Okay. Yes.
So will you have us be doing both methods on the quiz tomorrow?
No, I'm just going to tell you to get the inverse.
Okay.
So you can use whichever method you want.
It's gonna be one inverse.
You'll have to just come and find out. Okay. All right. So with that, then let's go ahead and try one of these. Okay. Let's say A is the matrix 5, 10, 2, negative 3.
Yeah.
Okay. Let's just make sure everyone can get started on the right foot here. How would I set this up?
Wait, which one?
Let's use the second.
Using the one that we just did.
5, 10, 1, 0, I mean,
Two negative
Yeah, that's right. 5, 10, 1, 0.
2
1,
negative 3.
0, 1.
Okay, good. So you see here, you have the original matrix on the left, the identity matrix on the right. You want to get to where you have the identity on the left and something we don't know yet on the right. Okay, so take a couple minutes here and try it out.
came
I did, yeah, 10 minus a negative 6.
Oh, okay.
You may have done it a different way, so your
Yeah.
numbers along the way may be a hair different. Okay?
What's the last one?
I got
Oh, what's the last number here? Let's see, 16 times 2 is 32, so minus 32, so that's actually plus. Hang on. What are we doing here? Row 1 minus 16. Oh yeah, so 16 times 5 would be 80. So that's a plus 2 and 5/35, or 1/7.
I got,
So that would be
I got
That's
negative,
2/7.
I
2/7.
got, yeah, 2/7 for the top and then negative 1/7 for the bottom.
The bottom isn't the 1/7.
Yeah.
Oh, yeah,
Hang on, what did I?
yeah.
Oh yeah, 5/35.
three.
Yeah, sorry. That's why I'm in trouble with it. Yeah, negative 5/35 is a negative 1/7. There we go. So yeah, that makes it a lot easier. So that'd be 16/7 minus 2, which is 14/7, so that's 2/7. There we go. Okay. So your inverse would equal 3/35, 2/7, 2/35, and negative 1/7. Okay? And no, you should not use decimals and round. Okay? Otherwise you don't actually have the inverse. You have an approximate inverse. Okay? Alright, so let's just step through this. I know I didn't really explain. Okay? First of all, you could have divided this by 5 right off the bat.
Yeah.
You could have divided row 2 by 2 right off the bat and switched the rows to get your 1 there. Or 5 minus 4 is 1, so I did row 1 minus 2 row 2 to get my 1 there. Any way you do it would work, okay? Now, once you have the 1 there, then we need to subtract 2 to get our 0 here. So I did row 2 minus 2 row 1. Okay, of course being careful with your arithmetic. Then, to get your 1, remember this is, this is our last 1 that we have to get. The only way you can do it without messing up the 0 in that row is to simply divide by what's there. So we divide by a negative 35. And we get 1 positive 2/35 and a negative 5/35, which is a negative 1/7. Okay? Then, since we have a 16 here, we need a 0. We subtract 16 of row 2. And just be careful with your fractions, okay? 16 times 2/35 is 32/35, so I subtract that from 1. 35/35 minus 32/35 is 3/35. And then we have 16 times 1/7, which would be 16/7, which is 1 and 2/7. Okay? Or I'm sorry, 2 and 2/7. So if I have 2 and 2/7, I'm adding that to a negative 2, I get positive 2/7 left over. Okay, so there's our inverse. Alright? Make sense? Kind of a pain when you get fractions like that. But here's the thing, it works. It works, okay? No matter what the numbers are, you're big boys and girls and you can handle fractions. Okay? Alright? So, here's the thing, is there an easier way? For 2x2s, yes. For 3x3s and 4x4s, no, without a calculator. Okay? So, but let's learn the easy way to do 2x2s. Okay?
The third way. So if we have 3x3 more, we have to use calculator basically.
No, if you have 3 by 3 or more, you don't have to use your calculator to do it. You can actually use this method
Do you recommend we do?
or this method.
You recommend we do the first, the
Okay.
second one?
I think the first
I-
one is easy.
Personally, I would do the second one.
This is the easy one. The second one
Okay.
is so easy.
So
You
it's
still
up to
get-
you.
get
If you
9 equations.
Huh?
This one you get 9 equations.
Yeah.
So,
Now, you'll get 9 equations, but you'll also, it ends up, I think you end up getting 3 sets of 3 equations with 3 variables. Just like here we got 2 pairs of 2 equations with 2 variables. So it's not exactly as hard as it sounds, but it's still not easy or fun. Yeah. So I personally would do this. Okay. Well, let's look at our last method, and this only works for 2 by 2. All right. And what we have here is called a determinant of a 2 by 2. All right. And here's where we're gonna look at determinants again here in the near future, but this method relies on the determinant of a 2 by 2. The notation is this. Okay, the notation for the determinant of a 2 by 2 is that symbol right there, which, guys, you've seen that notation in a lot of different contexts. Okay, in one context it means absolute value, in another it means distance, in another it means the magnitude of a vector. Here we're talking about the determinant of a matrix. Okay, so context is really important here. But what we're doing to find the determinant of a 2 by 2 matrix is we kind of look at the 2 diagonals of our matrix, A and D, and we're going to multiply A times D. And then we look at this diagonal as well, the B times B and C. We're going to multiply B and C, and then we're going to subtract them. Okay? It's actually a really simple process here. We find the determinant of A. Now, if you learn the pattern, you actually don't even have to memorize the formula so much. Okay? I like to call this the fish method. Alright? You're going to multiply forward, or add forward and subtract back. Okay? Go on the diagonal going forward, that's going to be the positive, or the one that you just leave whatever it multiplies together. And then, on the backwards diagonal, you're going to subtract it.
So AD minus BC.
Okay? So, AD minus BC.
I think I
So it kind of looks like a fish, alright?
Yeah, fish makes it more confusing.
Yeah.
Okay?
It's a fish. Yeah.
No, it's
So,
a fish though.
The fish method. Alright, so we have our determinant of a 2 by 2. Now, your book at this point doesn't introduce this as the determinant, but I'll show you the formula that they have, okay? And I'll give you a little simplified version of this. They have the inverse equal to 1 over this, which you guys recognize that now as the determinant, okay? Let me get rid of this so we can actually write.
Make it invisible.
Okay. I just used a white pen. So. All right. So really, our formula is this: 1 over the determinant times, and you'll notice I modified the original matrix. It's no longer A, B, C, D. It's now D, negative B, negative C, A.
Is this the? I don't know.
It's just a pattern that you got to memorize. Okay. Now, someone describe how we changed it, because
It's the not transpose, but like kind of like.
yeah, it's not quite the transpose, because it's kind of transposed and flipped around and some other stuff. How could you describe what we did to change matrix A to this matrix? Gosh.
Okay, so if you have a piece of paper that's a square and you put your finger on the top left corner, and then go like that, that's
Okay.
your thing. And then those two are negative.
And then those two are negative.
You reflect it over
You
the
go
x,
like
y.
this.
Except B and C didn't change position, right?
You reflect it over the x equals y.
Okay. You reflected over the x equals y line. That. Yeah. Okay. Basically, we're just switching the A and D, and we're making B and C negative, right? You switch A and D, and you make B and C negative. Okay?
Why?
Huh?
Why?
That's just the rule here.
That's your answer.
Okay? That'll be your answer. Now you will want to distribute the value in, but yeah, that'll be your answer. Okay? Let's see this one in action. This is the same one that we've already done twice, so we ought to get the same answer, right? But let's first of all find the determinant of A. What's our determinant of A?
A, B minus.
Negative 3 plus 4.
Negative 3 plus 4. 1 times the negative 3. That's your forward diagonal here. And then we have to subtract the backward diagonal. So minus 4 times negative 1. Okay? So that's negative 3 plus 4, which is 1. Okay? So now, my inverse is going to be 1 over 1, just use the formula, times, what's the matrix going to be that I'm going to multiply by the determinant?
Negative 3, negative 4, 1,
Negative 3, negative 4,
1.
1, 1. Notice I switched the negative 3 and the 1 here. Okay? So you switch these, and then you make both of these their opposite. Okay? And you'll notice, obviously we're just multiplying by 1, so it's negative 3, negative 4, 1, 1. And that is our inverse. Okay? Yes?
I'm curious why, like, you said we tried this 3 times. Why did we get a different answer for the
Echelon form?
form?
We didn't.
But we got like 3 over 35.
No, that was a different example.
Oh, okay.
That was a different problem. Which actually we're going to do again this time, and we should get the same answer using this, okay?
You're done.
Before we do this, ask me, or tell me, why would it be best to always find the determinant first before you do anything else?
So
If you didn't
can
get it
divide.
wrong, everything's wrong.
Well, if we do that wrong, then everything's wrong.
So you can divide. So maybe if it's 1,
I don't know. I'm guessing there's other uses besides that.
Okay. Well, think about what you're saying. If it's 1, it's a really easy problem.
oh, so maybe, so imagine it's 2, you can do like right from the start, you can do d over 2, you can do d over 2.
Yeah, you could. Alex?
How would we not do the determinant?
Well, I mean, before you even wrote down what the other what
Because if
this
it's 0,
matrix
it's
is going to be.
undefined.
What?
Because if it's 0, it's undefined.
If it's 0, it's undefined, and you can stop right there. All right. It is possible. Listen. It is possible to have a matrix with no determinant, okay, or with no inverse, and that happens if the determinant equals 0, okay, because you'd be trying to divide by 0 here. That's why this method is really, really nice. If we tried to do this with echelon form, and you had a 0 determinant, you'd get one of those forms where you had like 0, 0, and so on, no solution. But here, if you get the determinant equal to 0, there is no inverse if the determinant equals 0. Okay? It's undefined. Yes?
Could you come in for the video? So after you get to this part.
Oh, on the
Well, this is just 1. So technically you have to multiply everything in here by
the matrices and then that's it.
yeah,
And so that's the
and that'll be your inverse.
that stuff on the bottom.
So, well, here I multiplied 1 over 1 by the -3 and still had -3.
Yeah, but the thing on the left.
This? Oh, that was finding my determinant.
That was before you did.
That was before I did anything. That's how I got the 1 to go here.
Alright.
Okay. Alright, so you guys found that, listen, you guys found that this problem was a real pain to do using echelon form. Let's do it using this method. Okay?
What are the numbers?
5, 10, 2, -3. Okay? Try finding the determinant first. Remember, the inverse is 1 over the determinant of A times D negative B negative C A.
Oh, yeah, that's easy.
Yeah.
It just doesn't work.
That's beautiful.
Mr. Harrison, do you know how to fix laptops by any chance?
Depends what's wrong with them.
The battery's just not working.
Yeah, open up, take the battery out, and put a new one in.
Can't do it with that.
I don't have
Unless you dig it out.
You can, you just need to
You need to unscrew it.
specialized
We
tools.
can't
And,
talking about
Sometimes it happens in mine. It like it wouldn't turn on for a day, and then you just like decide like hey, I'll work today, and like it worked again. So
Yeah,
Maybe that'll happen.
if we would have more, I'll show you.
all right, hey, what do you get for the determinant?
-35.
-35. All right, you have a -15 minus 20. Okay, -15 minus 20.
Fish.
Okay, so we have a -35. What's the matrix we're multiplying 1 over -35 by?
-3, -10, -2, 5.
Good. We switch the -3 and the 5, make the 10 and 2 negative. Okay, so now you just have to be careful with your arithmetic. Positive 3/35, positive 10 over 35, which is 2/7, positive 2 over 35, and then negative 5 over 35, which is a -1/7. Okay,
It's much faster.
much faster.
Yeah.
And with 2 by 2 matrices, this method is pretty much always going to be the fastest method you'll use. Okay.
Is there any reason why it's DBCA
Basically, the way formulas like this, guys, listen up, please. The way formulas like this end up being developed is people do it the hard way a bunch of times, and then eventually realize that there's a pattern. For instance, they might have seen a number of ones like this, and they say, hey, we keep having it over 35, and the sevenths were 35ths before we reduced them, so maybe there's something to do with that 35, and then they realize the determinant was 35, so they say, okay, well, what would we have if we factored that out? You know, and that's how formulas like this get developed, is they just do stuff over and over and over again until they recognize a pattern. Kind of like the quadratic formula. you guys have solved stuff with completing the square. The quadratic formula is just the result of completing the square. Okay, it's derived from that process. So someone did it with A's, B's, and C's instead of numbers one time, and then simplified the result, and they said, hey, here's
Didn't we
a
derive that
formula.
formula?
Yeah, we went through the derivation of that, so.
And then now he's rich.
Huh?
Now he's rich.
Now he's rich, now he's probably dead.
Yeah, but
So, yeah, I don't know who did it first, so. Alright, so let's take a look at another thing, how do we use the inverse, okay? One thing that we can use the inverse for is to solve systems of equations, okay? Systems of equations can be written as a matrix equation, which we'll look at in a second. But take a look at this equation here. We have matrix A times matrix X equals matrix B. Alright, and we want to figure out what matrix X is. Okay? So, you guys know that in order to, when you have multiplication with numbers, you multiply, you divide, which is the same as multiplying by the inverse. You're multiplying by the reciprocal of a number, which is the inverse. Okay?
Times 1 over 8.
So what?
B times B divided by inverse of 8.
Well, here's the thing. We can't divide in matrices. We can multiply
Multiply the inverse of 8.
by the inverse, okay? So here's what I'm going to do. On this side of the equation, I'm going to multiply by the inverse of A, and because matrix multiplication is associative, I can group the A and A inverse together. Okay? Now what do I do?
Oh, you get 1.
We get
1, 0, 0, 0.
1, 0, 0, 1, or whatever the identity matrix is, right? Okay? We get the identity matrix.
But don't you put it on both sides?
We do have to be fair to both sides. Okay, I'm actually gonna bring this down. A x equals b, so we can see the same original equation. So what's gonna be on the right hand side?
Inverse A times B.
What?
Inverse A times B.
Inverse A times b. So I can write it. I can just write that, right? Can I write that?
Yeah.
So I'm gonna go with no, because otherwise you wouldn't be asking.
Yeah.
Why can't I write that?
Because the order matters.
The order does matter. Exactly.
I know, of course.
Of course, yes. Alright, the order does matter. And actually the way Thomas said it originally is correct.
That's how I wrote
You would need to put A inverse times B. And the reason again is because the order matters. On the left hand side, A was on the left, so you had to put the A inverse to the left of it. Okay? So over here, you have to do the same thing. Okay?
What if you want both on the right?
Well, if you put it on the right, then it wouldn't be next to the A, so you wouldn't be able to get the identity. It would be on the right of the X. So yeah, no, I mean, that's a valid question. I mean, you can't just stick the A inverse in the middle here or something, okay? Because again, order matters. But here, now that you have the identity times X, you guys know that's just X, because that's what the identity does. And that's going to equal whatever the inverse of A times B is. Okay?
And you can do the opposite if you want to find A.
Yeah, you could do the opposite if you wanted to find A. You'd have to use X inverse. And in both cases, X inverse would have to be on the right side of your product.
Okay.
Okay? Yeah. So let's look at how we would write this type of equation for a system of equations and then actually use it. We're only going to be able to write it, I think. Oh no, we have 5 minutes. We're good. Let's say we have a system like this. When I write this as a matrix equation, what we're going to do is we're going to have a coefficient matrix first of all. Okay, what would our coefficient matrix be?
3, 4, 11.
3, 4, 5, negative 7, right? Just the coefficient matrix, not an augmented matrix this time. Okay? Then, we're going to have our variable matrix. It's going to be a 2 by 1 matrix because it just has x and y in it. And we want to figure out what that x and y are. Okay?
Equals
That equals
11.
a 2 by 1 matrix, 11, 9. 11, negative 9. Okay? So, what we need to do is find the inverse of 3, 4, 5, negative 7 and multiply both sides by that value. Okay?
So should we use the determinant?
So, yeah, let's go ahead. I'm going to call that A because we want to get A inverse. So, first of all, the determinant of A is what?
Negative 41.
Okay, a negative 21 minus 20, negative 41. Okay. So my inverse is 1 over negative 41 times
Negative 7 plus negative 4, negative 5, 3.
very good. Okay.
Oh, yes.
So if we write that, we have positive 7 41sts, and you're thinking 41sts. That's wonderful. Positive 4 41sts, positive 5 41sts, and a negative 3 41sts. Okay? That right there is our inverse. Okay? Let me shrink that up a little bit. Okay? That's our inverse. So, when we go to multiply both sides of the equation by this, do this, speed things up, okay? When we go to multiply both sides of the equation by this, we're going to have,
Oh, that's me not.
okay? It's actually not as bad as you might think, okay? We have 7 41sts, 4 41sts, 5 41sts, and negative 3 41sts. Now, do I need to do this matrix multiplication? No, because it's the identity.
1, 0, 0, 1.
Yes. Alright, so in the end, this whole left-hand side just equals x, y. Alright? Because again, this is the identity. Okay? But on the right-hand side, we will have to multiply. Okay? Okay? Now, again, it's not too bad. Alright? Not too bad. So, let's do the matrix multiplication. You have 7 41st times 11 plus 4 41st times negative 9. So 7 times 11 is 77. 4 times negative 9 is a minus 36. 77 minus 36 is...
Oh,
Negative 29. No, it's
Negative
not.
1.
It's
It's 1.
Yeah, that's 41, right? So what's 41 over 41?
1.
1, okay? So we know now that x equals 1. If we do the y, we have 55 plus 27, which happens to be 82. What's 82 over 41? 2.
X.
So x equals 1, y equals 2.
I'm just gonna guess some check.
Okay.
Yeah.
So we have. So Mr. X, what the please?